Okay, we're looking at compound interest today. Previously, we'd taken a look at simple interest. Simple interest went like this. It was that your interest equals your principal times your rate times the amount of time that you were in, and your account balance equals your principal plus I. That's old. That's what we previously looked at, where what they do is they pay you interest based on how much money you gave them eventually at the very beginning, and every time they pay you out, they pay the same amount because it's only based on how much you initially gave them. Compound interest allows interest to pile up in your account by adding to the balance before the next interest payment. In general, if you have an interest payment in annual interest, and this isn't very useful by itself, but it will get us off to a start to look at the difference between compound interest and simple interest. The formula equals that your account balance is going to be equal to your original principal times this thing called 1 plus R. R is still going to be your periodic interest rate times the number of years that you did leave that money in. So if you deposit $10,000 into an account that pays interest annually, at 10%. Find your final account balance after 25 years. Use A, simple interest. And they might pay you 10% simple interest on a bond. Or B, compound interest. Let's say that you didn't loan them the money, you bought stock in the company. And the company's value went up by 10% for stockholders every year. What's going to happen is they're just going to pay you 10% of your $10,000. They're going to pay you $1,000 every year for 25 years, and you're going to get your $10,000 back. So A, account balance is equal to your principal plus your interest. Now, what we found from them is that your principal is $10,000. Your value for interest is going to be once a year, and it's going to be 10 divided by 100, and it's going to equal 0.10 or 10%. The amount of time that it's going to be in there is going to be 25 periods, which are 25 years. So what we get for the old simple interest is we do begin with you get your $10,000. Let's see, you put in 10,000, and so I will mark it up properly. 10,000 plus you get 10,000 times 0.01, times 0.10 times 25 years, which this is 10,000, and that's 25,000. And over 25 years, if you go back and get it, you're going to have $35,000. What's the benefit of that is you can take the $1,000 every year that you generate in interest, and you can go spend it right away. You don't have to wait to go back and get your money. So every year you get $1,000, and at the end you get your $10,000 back, and that's what's money that came out from them. But the money that you invested in the first year churns out $1,000 for you and you take that money and spend it. What you do if you go for compounding is you say, buy me more, right? Buy me another bond that's going to pay me 10% of this. And every year you take all the money that you get from the bonds and you buy more. More likely though, compounding would be something like an investment that on average returns you 10% compounded. And let's look at what that does using our formula right there. The account balance is equal to, you're going to take your $10,000, you're going to multiply it by this number, this factor. A multiplying value is a factor. You multiply by this factor every year for 25 years. And what you're having here is 1 plus R is 0.10. So 0.10. And you do that 25 years in a row. So you're going to multiply it. So it's going to be like $10,000 times 1.1 the first year, next year times 1.1 times 1.1 times 1.1 until 25 years are done. So this is going to get you $10,000 times 1.1 to the power 25. So you should probably go along with your own. You can see how that one generated the 35,000. We had a pretty straightforward value for that. But this is $10,000 times 1.1 powered to the 25th power. And we're going to hit equals on that. And let's see what we got. Yeah, don't trust the dollar store, right? Let's make sure. 10,000, 1, 2, 3, times 1.1, don't hit equals, powered, hit the wrong button again, so yeah. Well, let's go 1.1 powered to 25 equals, and then we'll multiply that by your 10, 1, 2, 3. And you got 108,347 before we hit the decimal. .059, so 0.06. So we also have that 6 cents. Same interest rate, same amount invested, same amount of time. One was paying you interest only on the original 10,000 every year, and it paid you a steady $1,000 a year for 25 years, and you got 35,000. Compounding took the money and rolled it back in to allow you to build interest on your interest, and that returned you over $108,000. So more than 3 times as much. And that's the power of compounding. It is alleged that Warren Buffett called it the 8th wonder of the world. I doubt that it was him. It's probably an urban myth. If it was him, he probably wasn't the first. But I'm sure he's impressed by it. Among other things, what he said, people say, Warren, what should we invest in? What are you going to do with your fund when you die? He said, oh, that's easy. I'm going to put my fund in an S&P 500 fund. I'm not going to try and have someone else pick stocks. I'm just going to have them put it in there, hope for 10% a year, and just let it grow. So instead of being out there trying to find the next great investment and nail it as one stock and get rich by allegedly being so smart, he's going to trust the entire market to do well and grow over time and hopefully deliver him 10%. And that could be a real number that could be achieved. Some people kick around the number 6%, which is kind of the growth of the value of the stock. Then you add in dividends and other things like that. And somewhere between 6 and 10% is what you can say has happened for over 100 years on average. So, you know, if you can get a good return, the things you can control, how much do you put in, how long do you leave it in, that you have control over. What you pick is the gamble that you take as to what stock or what fund you're going to invest it in. But here they are, both at 10%. And if you say, oh no, I just definitely want to get my money every year, I don't want to go for the ups and downs of the market, I'm too nervous, then you can have the $35,000 under this plan. If the market does 10% on average every year, including dips and all that, but averages a 10% gain, you'll have $108,000. It's the power of compounding. The thing about compounding is how often you allow it to compound is going to change your interest rate, how it's going to get what we call the periodic interest rate, and that will impact how many times you get to use that multiplier. And you'd think, you know, if I get 10% per year and it compounds, then that's going to be the same whether they do it monthly, daily, weekly, whatever. That's not true. It tends to be that the more, and it is definitely true, the more frequently you can get people applying the interest formula, the better off you'll do. But it does not go up to infinity, and we'll see why that is. Here's the formula that we're going to have. The account balance is equal to your principal times 1 plus capital R to the n. And I'm going to use these things throughout the rest of the course for the formulas that I use. The book uses a different type of formula. They like to have lots of things like capital N, lowercase n, capital Y, lowercase y, and all that, and want you to know the difference and apply them appropriately and all that. Through the years, I've gone through the process of saying if we do this on a periodic basis, it's going to be more concrete and easier for people to deal with. So you can look up the formula in the book and use the formula in the book and on Connect Math, and it'll do the same job. But they make you keep going back and they say, well, what is this? Where I have capital R, they have your APR over 100 and then divided by n. What do I have? I have, let's get R set up to be the APR, which is a percentage, divided by 100 because it's a percent, and then divide by n. How many times a year do you use that annual one? N has a few values that are important, and I'll put those on the board for you shortly. The number of periods they call n times y. How many periods per year do you do it? And they multiply it by y for how many years, or even t they might use. But y is the number of years. And it might have a decimal to it, but that's okay. Because for time, I want to know how many years is it in. If it's in 20 years and you do 12 payments a year, that's 240 payments. The more familiar one might be 30 years at monthly payments, 360. That's your classic 30-year mortgage. Car payments, I don't know, 5 years. Somebody always tells me, oh, I got one for 7. That means they're going to be paying for a car till it's 7 years old. It'll be nearly worthless in most cases, but okay. The thing is, n is how many times per year you pay it, and y is how many years. That 7-year car loan is going to be 84 payments. 5 years, which I tolerate for a brand new car, 60 payments, okay. 3 years, which I recommend maybe for a used car in most cases, 36 payments. Just because I don't want you having a loan being paid on a car that's really old and you're still paying for it. But they do allow this because what happens, it drives the payment down, and people are like, oh, I can afford that. And for 7 years, they make that payment. And they are so sick of that car sometimes after 7 years, but there you go. We'll look more at that toward the end of the course about how to deal with those options that you get to choose. Pick what's good for you, but I'll try and lay out the facts of what's going on. So what we're going to do here is I'm going to lay out for you what I'm going to use throughout the semester. Okay, A is going to be your account balance. What we're going to look at for now, P will always be the principal. Okay, it's a PAL kind of thing. That's how we spell that, principal. When we do a payment, we may see that we're doing a payment. We may have it be something other than principal. But for almost all our work here, we'll have P as our principal. P is always your own kind of money going in. Okay, next thing we're going to do is we're going to look at R. Now what that's going to be is going to be your periodic interest rate. That means every period, how much do you pay as an interest rate? But it's important that we know how to do this too. All right, I'll put that P in capital, P from principal, R from rate. This is equal to your APR, which is not 3 multiplied values, but it's annual percentage rate, divided by 100 and divided by n. Here are values for n as promised. N equals payments per year. N equals 1, we call that annual, that's once a year. N equals 12, we call that monthly. Every month you make a payment, that's going to be 12. N equals 52, then we're going to call that weekly. It's actually not 52. If you take 365 and you divide it by 52, you can find there's a little bit extra on there. We don't have exactly 52, but that's what's standardly used. 52 weeks a year. Daily, unless you talk to someone in the military, then they'll say something. I remember hearing from military. The military is on duty 365 and a quarter days per year. What he was saying to that class when I was there in 8th grade was that the military is on duty all the time. They are even there on leap day. Because 365 and a quarter is going to account for leap day. This year, if we only did 365 days, we would finish at the end of December 30th. But we go with 365, and it works out because Whatever number you use to divide is going to come back in how many payments you have to make. This is my capital N. It is your number of payments. It's the total number of payments. And what does Connect Math have us doing with that? It says you take the number of payments that you make from there, those are probably our most common features, and you multiply it by Y. And Y equals the number of years. But we're going to use this throughout much of what we do. We're doing it with simple interest, where we had APR, right? And then we had N could be the number of payments, but if you paid yearly, then no big deal. And you know, the periodic rate is not needing to be sliced into a lower rate when you deal with simple interest. You don't have to say, oh, I pay monthly. Well, it doesn't matter. It's just because it's so flat, it doesn't matter how frequently you make the payments. But it does change when we do this with compound interest, because what we put in here, the interest rate is going to be smaller after we divide it by 100 and divide it by lowercase n. We're going to have up here is going to be bigger than the number of years, because you're going to multiply it by how many times per year, right? So you're going to multiply the years times how many times per year to get your total number of payments, and that's how many times you're going to hit it with that multiplier. And every time you hit it with that multiplier, if it's greater than 1, you're going to see growth in the value of the account. And it doesn't come out evenly. So I want us to do this. I have those, and I want to slide them in to say what I've just written on the board, so it'll still be there and available for us. But for what we have, we're going to go and look at assessments of compound interest. Okay, that we can still use. The account balance is equal to the principal times 1 plus R. That creates our multiplier to the value of N. Now what we want to do is these things in succession. Determine the account balance of $1,000 deposited at 10% APR, 10% is your annual percentage rate, after 9 years. And we're going to do it in 3 ways. We're going to go annual, monthly, and weekly. We won't do daily, but we certainly could do the same process with that. And you could get it down to the point where it's doing it every hour, minute, second, millionth of a second if you wanted to. But we're going to look at the value changes of what happens to the account value if they just apply the interest annually, or every month they apply, instead of doing the whole interest rate, they do 1/12 of the interest rate on that 1 plus R, and then do that 12 times a year. What about weekly? What if they do 1 over 52 for that interest rate? Much smaller interest rate, but they do it 52 times during the year. Those two numbers are the same. Whatever you're using for how frequently you're applying interest shrinks the rate and increases the frequency of the multiplier being applied. So what we have here is A in each case equals, and we always have $1,000. And we always have 1 plus. And then we apply the 0.1. 10%, right? 0.1. If I want, I can divide this thing by 1. I don't need to, because it's only applying once per year. So then I'm going to apply this thing up to something that is going to be my number of years, which is 9 years times 1. I'm going to leave that in parentheses. It's just 9 times 1 is going to get me 9. What happens on this other one is it begins with 10%, which is already divided by the 10 divided by 100. And then this is going to divide by 12, and it's going to go with 9 times 12. And this one is going to take the 10% and it's going to divide it into 52 equal wedges and apply that factor 52 times. So I'll get it to the nearest penny for us. It's a 9-year process. Let's see how much of a difference it makes to have it compounded annually, compounded monthly, or compounded weekly. If it were simple interest, we wouldn't have to do this. There'd be none of that impact of how frequently interest occurs. But on the first one, I'm going to go with 1.1, and I'm going to power it to the 9th, and that's times $1,000. 1, 2, 3. And I come out of here with this 2357 and 95 cents. I just left the money in for 9 years. I went back, I could pick up that. Doesn't sound bad. Let's try the next one. What I have is 1 plus, I'm doing the inside of the parentheses, 0.1 divided by 12, and I've now just created my factor. It's 1.00833333. I don't clear it, I don't type it, I let it sit here to take full advantage of as much memory as this has for accuracy. And I'm going to raise that to the power where this is 108. So I'm going to raise it to the power of 108, which is 9 times 12. And out of there, I get $2,450.45. All that they did was apply the formula more frequently. Nothing else changed. I made close to $100 extra just by having that. Now we'll go for weekly. I'm going to go do the inside the parentheses and do 1 plus 0.10 divide by 52. I'll take a look at what that is by hitting equals. 1.001923077 is as far as my calculator goes. I don't need to write that. I'm going to let it retain its value here. But now this is 468. And I could certainly find that before I entered it. I could even raise it to that power if I use my parentheses. But what I have to do is raise this factor of 1.00 something, so it's going to grow 468 times over the length of this loan. So I raise it to the power of 468 equals 2457.4, let's see, 8. So doing that, compared with monthly, it made me about $7 more over 9 years. A little bit, but not much. So this may give you the impression that this is something that goes on, that if I let them do it infinitely many times and cut it into infinitely small slices, this value would turn out to be infinite dollars, but it's not. It caps off at something involving limits and calculus and all that. And if you've ever seen the formula, if you want to know what it is when you do continuously, it involves limits. And just for the benefit of people who have ever taken calculus, I'll say if the value of this were taken continuously, then we have A equals P times E, that is the lowercase e from the natural log, if you're familiar with it, of the interest rate times the time. So it's going to get for me here the number of years times R. So this is 9 years times 0.1. And so what I have here is when I put in my $1,000 and I rely on what E does, so I use E on my calculator, Y is the number of years, which is 9, and the interest rate is 0.1, so I'm going to go to the 0.9. And this tells me if they went to what the limits of what this curve would do, let's see what we get. I'm looking for the natural log. I found it. I go second function of the natural log, creates my value for E. Let's see. Second, oh, I want to get my value of 0.9 in there first. I want to get E to that power, so I'm going to go second function and get E to that power. And I'm going to multiply it by 1,000. It's as good as it gets. When you stick with the same values, 24, 59, and 60 cents. And I'm not going to go into the details specifically of how that happens, but that's as good as you can do with those numbers, as if they were doing it based on the limits set by calculus. But you'll see that the more frequently you do the application of your interest, the better it is for you. So you want them to do it a lot. So if you can get compounded daily, you'd prefer that to compounded weekly or monthly or annually, because compounded daily will get you an even better return. Somewhere between here and here. So we're looking at over the course of 9 years, you're going to make some of that $2 difference. So it's not huge for this little amount, but it does add up when you get to big values. So I want to take a look at some really important numbers for you, just to have you think about it. Because if you're, let's say, planning to retire at age 62, and you're currently 22, and you want to know how much money do I have to put in the bank if I could get 10% per year, which is not easy, but if on average I could get 10% per year compounded annually, how much would I have to put in to be a millionaire? So how much must be put in an account now at 10% APR compounded annually? Let me see, did I do that compounded annually? Sure, let's go compounded annually, no big deal. Be better to do it monthly or something like that, or daily be better. For 40 years. So that it's worth $1 million. At the end of those 40 years. Let's see what information we have here. We don't know the principal. We know A, it's got to be $1 million. We know that we're going to get an interest rate, which is 10% divided by 100, which is 0.10, 10%. And N is equal to 40 years. So we don't know the principal. Now what we have here is A equals P times these parentheses, 1 plus R to the N. We'll divide by the parentheses to the N. Cancel the parentheses. And P is equal to A divided by 1 plus R to the N. A is $1 million. 1, 2, 3, 4, 5, 6. 1 plus 0.1 is 1.1 raised to the power of 40. So let's see if we can do that. The top's $1 million, let's let that wait. Let's figure out what 1.1 to the 40th power is. 1.1 raised to the power of 40 equals, I got 45.26 approximately. 45.26. On top still sits $1 million. What that means right there is each dollar that you put in now, if you get 10% for 40 years, is going to be worth $45 and about 25 cents, 26 cents in the future. So I'm going to go ahead and do that division. 1, 1, 2, 3, 4, 5, 6. There's my $1 million. And I'm going to divide it by 45.26. I don't know if you grasp what number this might turn out to be. I'll put some digits up there. 220946. It's not $2. It's not $22. But it's something up there. The decimal goes somewhere. All right? You might think that this is saying that you got to put in, I mean, I sure hope you don't have to put in $2 million to have $1 million. You might think that you have to put in $220,000 and $945.60. But in reality, what you're going to have to do is put in $22,094.56. That's real. If you can get 10% return over 40 years, if you were able to put $22,000 in, you'd be very close to a millionaire just from that money 40 years from now. That's what compounding does. Perceive that now, okay? Now the great thing is when you're 22 years old, can you get $22,000 together? If you're like I was, the answer is absolutely not. You can't go up to Grandpa and say, hey Grandpa, you know, can I have my 22 grand now? and let me put it in the bank, not in the bank account like a CD or something, but let me try and put in an investment that makes 10% per year. If you could get hold of this $22,000 and put that in the bank right now, it'll be $1 million in 40 years. If you get 10% return. That's not easy to do. You got to manage risk to find something that'll return that. There's no guaranteed 10%. What I heard about a policy, a practice that was offered to only to the ultra wealthy was a promise of 14% per year. And only a few people were invited to get in, and everybody wanted to get in for 14% per year because of what it did, how their wealth grew so quickly. You may have heard the individual that ran this account. He lived right down the street from Norwalk Community College in Greenwich. His name was Bernie Madoff. He was promising returns he could not deliver, was running what was a Ponzi scheme. If we were doing projects this semester, I'd direct some of you to consider doing a project on that. But projects are optional this semester. You could still do Bernie Madoff's Ponzi scheme if you'd like. It is a good way to help boost your grade, especially if you don't like where your test scores are. But 14% was not something he could really deliver. It was a scam. And he went to jail. And things did not end well. Although I guess he had a lot of money for some time and lived a high life. This is achievable. Now, how do you get 10%? I don't know. But that's what the numbers would say you would get. I mean, I have my guesses as to what I would try. If you look at what is being suggested as a way to deal with the money when he's gone, you can look at what the Sage of Omaha is saying. And he's saying, put it in an index fund of the S&P 500 and hope for 10% a year, because he said hope for 10% a year that you would do. So Warren Buffett said, don't try and nail the winners, try and make the power of compound interest work for you. So this is what compound interest is. I'm circling 10 years in a couple places on that same problem, because what I've done is said, you know what, I'm 22, I don't want to save money for when I'm 62, but I do want to be a millionaire. So I think I'll do this thing. I'll have fun until I'm 52, and then I'll really buckle down and I'll put a big chunk of money in the bank. So I'll have the million when I'm 62. How big will that have to be? So if you decide, you know, that's what old people do. You save for retirement when you're in your 50s and you get to be 52, which is younger than I am now. So if I tried this plan, I would need more. But here we go. The only thing that changes is the 10 years where the 40 used to be. So we still have the $1 million up there. And I'm going to put in 1.1, but I'm only going to do it for 10 years of compounding. So I'm going to put in 1.1, and I'm going to power that up to 10 years. And the number that shows up in this case is 2.5. So we got $1 million. And we're going to divide it by 2.5937. Maybe that's enough accuracy. Anyway, we'll certainly get a good idea of what you need. So we're going to take the $1 million and divide by that. So we'll go 1 million, 1, 2, 3, 4, 5, 6, and we're going to divide this by 2.5937, and it's going to equal for me 385,549. And some of those are going to be the numbers that we have to have. But here's the news about that. Comma, period. If you want to start when you're 52, instead of dropping in 22,000, you're going to drop in over 385,000. Because that's the power of compounding, which is powerful, especially as it gets to climb into the later years when you've been building it longer and longer. So you want to start early. If you could get 22,000 in at age 22, you'll get to that million. If the numbers are the same, but you only get to start when you're 52, you need to somehow have amassed $385,549.60 to get yourself to the million. So my encouraging words for people like this is try and get that money in there, but it's really hard to get $22,000 scratched together right now for someone your age. What we're going to look at when we look at annuities is, what about if I just put money in every month to get there? And that'll be in our later lecture. It'll be in lecture 22. So that's a word about compounding. Good luck. Okay. Let's get over the shoulder on this. That's what, gonna have like 3 minutes?
Not even.